Hello everyone, this is the 10th week class. Today we are going to study a technique called structural equation modeling. Suppose that we want to examine the relationship between satisfaction and performance, right? For example, we want to check the relationship between satisfaction and performance like this. So we are expecting that satisfaction affects performance, right? Now in this case, the technique that we can use is if satisfaction and performance are measurable, then we can use a regression, right? So P is like right? If these ones are measurable, right? But unfortunately, performance and satisfaction cannot be directly measurable, right? So how do you measure satisfaction? Now, usually what we can do is to use a some type of survey. You can create questionnaires, right? And then ask people about things, right? And then you get the data. Now in that case, so satisfaction and performance is measured by several questions, right? Question 1, 2, 3, things like that, right? In that case, these satisfaction and performance are called latent variables, right? These variables cannot be directly measurable, so these variables are called latent variables, right? In this type of situation, right, then you cannot use a regression here, right? So in this case, we need to use a technique called structural equation modeling, right? Now, the structural equation model consists of two things. One is called a measurement model, and the other one is structural model, right? Let me explain this by using an example. Now, this is an example of a structural equation model. There are three variables, EP, AC, and OC, right? EP stands for environmental perceptions. AC stands for attitudes toward co-workers. OC stands for organizational commitments, right? So here we see an error from EP to OC. That means EP affects OC, right? And also we see an error from AC to OC. So that means AC affects OC, right? And EP, AC, and OC are latent variables because they are not directly measurable. So they are measured by questions, right? So EP measured by 4 questions, EP1, EP2, EP3, EP4. And also AC is measured by 4 questions. And the OC is measured by 4 questions, right? In this case, this part and this part and this part is called a measurement model, right? And this part, the relationship among the latent variables is called a structural model, right? So SCEM consists of two things: measurement model and the structure model, right? Particularly, measurement model is called the confirmatory factor analysis, right? Now let me go back to the example. So as I said, EP, AC, OC are called latent variables, right? Sometimes they are called constructs, right? Latent means it cannot be directly measurable, right? And the questions, EP1, EP2, EP3, EP4, AC1 through AC4, OC1 through OC4, those are called indicator variables, right? Those are the questions that are used to measure latent variables, right? And EP and AC are called independent variables, right? Sometimes it is called exogenous variables, right? And the OC is called endogenous variable, which means dependent variable. Okay. Now, if you see this type of error, this is one way, right? So in that case, it is called a recursive relationship, right? Unidirectional, right? If you see this type of errors both ways, then it is called a non-recursive relationship, right? In our case, since these ones are unidirectional, right? So we have a recursive relationship here. And if you have errors like this and errors like this, right? Then non-recursive. This one is the error representing the correlations, right? It's not a non-recursive relationship, right? Now let's look at the measurement model here. Actually, this measurement model is used for confirmatory factor analysis, right? So measurement model defines the relationship between latent variables and indicator variables, right? And the measurement model is used to check the discriminant validity, right? So for example, if you have a cross loadings, then you can say that there is a lack of discriminant validity. So what are the cross loadings? For example, if you have loadings like this, right? These ones. These ones are cross loadings, right? If you have a cross loadings, then that's not good news, right? You should not have a cross loadings, right? So basically, discriminant validity checks, whether you have a cross loadings, right? So you should not have a cross loadings, okay? This is not good. And in our case, the EP affects OC and the AC affects OC. This one, the relationship among these variables is called a structural model, right? So today I'm going to show you how to draw, these graphs and how to get the estimates for the past coefficients and so on later, right? And before we do that, let's talk about some principles here. Basically, you want to find the relationship among the variables, right? So variables means latent variables, right? So you wanna get the estimates for the path coefficients. For example, EP to OC and AC to OC, right? Basically, you wanna get the values for the path coefficient, right? So how do we get the path coefficients? Just like the integration, you wanna get the coefficients, right? To get the regression equation, right? Just like that. In this case, we use a maximum likelihood estimates, and the principle for getting the path coefficients is to make the estimated covariance matrices as close as possible to the observed covariance matrices. This one is just like the factor analysis. Remember that you wanna find the factor loadings, right? Which makes the theoretical covariance matrices as close as possible to the observed covariance matrices, right? This one is almost the same as the factor analysis, right? Identification, this word refers to the situation where we can solve for the problems. Actually, when we do the maximum likelihood estimates, right, we create many equations, and actually we solve those equations to get the coefficients, right? If we can solve those equations, the multiple equations, then we can say that we don't have an identification problem. As I said, identification means we can solve the problem, right? So basically, you create multiple equations. I'll talk about this one by using an example later, right? And solve the equations for unknown variables so that the estimated covariance matrices are as close as possible to the observed covariance matrices, right? This one is the theoretical covariance matrices, right? And if we cannot solve equations for unknown variables, then we have an identification problem, right? If you have an identification problem, then it's a very serious problem, right? Because you cannot get the answers, right? So you need to do something to get the answers, right? Now, this one is a typical example of a structural equation model, right? So in this case, home affects aspire, and ability affects achieve, home affects achieve, and aspire affects achieve. It's very complicated now. And as I said, this one is just simply the correlation between home and ability, right? And home is measured by three questions, right? And ability is measured by two things. And aspire measured by two things. Achieve measured by two things, right? And you create equations like this, okay? For example, in this case, aspire is a dependent variable in this case, right? Because errors comes from home and errors come from ability, right? And these ones are the independent variables, right? And also this one is dependent variable, right? So aspire is a function of these ones, right? These two independent variables, right? And these ones are the path coefficients, right? And this one is simply the error, right? So you create equations like this, right? So you want to find, these ones, right? These ones. right? To make the theoretical covariance matrix as close as possible to the observed covariance matrix, right? So in this case, the theoretical covariance is very complicated, right? Let me show you a simple example, right? Suppose we have this, right? In this case, we can make a theoretical covariance matrix like this, right? Right? So actually, this is a theoretical covariance matrix, and then by using the actual numbers, you can create the observed covariance matrix, right? So you want to make, this theoretical covariance matrix as close as possible to the observed covariance matrix, right? As I said, if you have an identification problem, then that's a very serious, right? Serious problem, right? There are some ways which helps that we have identification. So usually you use at least three indicator variables for a latent variable, right? So it would be better if you use more than three questions for measuring a latent variable, right? And if you find negative error variance in the output, I'll talk about this one later, but variance should be positive, right? So if you have a negative error variance, then that's a very serious problem, right? Then actually you can change the negative error variance to a small positive number, right? Whatever the number is, usually I use, this number. So very small positive number, then, you can actually solve the identification problem, right? If you have only one indicator variable for a latent variable, right? Sometimes this happens, right? Then you need to set the variance of the indicator variable to 0, right? To make sure that you have identification, right? Now let's talk about the conformity factor analysis, right? So you know exactly, which questions are used to measure a specific latent variable, right? So once you know that, you do the conformity factor analysis to make sure that you have discriminant validity, right? So this can be done with Amos, right? So I'm going to show you how to do this shortly. And as I said, there shouldn't be any cross-loadings, right? In order to have discriminant validity, right? Discriminant validity is the degree to which measures of different traits are unrelated, right? Or is the extent to which a construct is truly distinct from other constructs, right? Construct is a latent variable, right? So make sure that you have, discriminant validity. To check the discriminant validity, you need to compute a measurement called AVE, right? AVE represents average variance extracted, right? This one is a measure of the amount of variance that is captured by a construct in relation to the amount of variance due to measurement error, right? Or it's the overall amount of variance in the indicators accounted for by the latent variable, right? So discriminant validity is secured if each of the correlations between two latent variables is less than square root of AVE of the corresponding latent variable. It's a little bit complicated, right? So let me use an example here. Suppose you have three latent variables, right? So A, B, C here. And you compute the AVE of A and AB of B, right? And you compute the correlations among these latent variables, right? So you take, in this case, you take the square root of AB of A, right? And you have correlations here, right? In this case, it's between A and B, and this one is correlation between A and C, right? These ones, should be less than this, right? So correlation between A and B should be less than square root of AVE of A, and this one also should be less than this, right? And this one should be less than this, right? This can be done by using the output from the confirmatory factor analysis, right? The formula for computing ABE is like this, right? I'm going to show you how to compute this one by using the actual output, right? So in this case, the standardized estimates here and errors, right? Standardized estimates and the error variances are obtained by doing the confirmatory factor analysis, right? Now let me show you how to compute AV, right? So we are going to use confirmatory factor analysis, and you want to make sure that there is no cross-loadings, right? As I said, these ones are cross-loadings, right? If you have a cross-loadings, that's not good, right? So you compute the AVE of each latent variable, and then you take the square root, right? And the correlations between the latent variables should be less than the corresponding square root of AVE, right? This is the output from the confirmatory factor analysis, right? So I show you how to get this, right? By using the Amos, right? Now you have estimates here. This is the path coefficient, right? And correlations here and error variances here, right? So you have, these ones. Right? So by using these numbers, actually, if you want to compute AVE for EP, then you use the standard estimates, right? So in this case, you use these numbers, right? So you square these things, and you add them up, right? So you have in the numerator, you have this. And in the denominator, you have the same thing here, plus the error variances, right? In this case, error variances are these, right? If you wanna get the AVE for AC, then you use, these ones, right? And you use these ones, right? And if you want to get the ABE for OC, you use these ones, and you use these ones, right? So you can get the ABE for each of the three latent variables in this case. Now, let me show you how to do the confirmatory factor analysis and also the analysis for the structure model, right? Now, in order to do this, you need to get the Amos software, right? The final exam is about the structure equation model, right? So I'm going to give you the data, and then you do the analysis by using Amos, right? So, you can get this software from the internet sites, right? Or you can go to the computer labs on campus, right? The data that we use for Amos can be one of the three types, right? The easiest way is to use the raw data, right? So once you get the answers from the people, right? You code, those answers, right? And so you, for example, in our case, EP1 and EP2, EP3, and so on, right? And these are the people, right? And you get the if you use either 5-point Likert scale or 7-point Likert scale, right? You have the numbers, right? And so on, right? And so on, right? This is the raw data, right? And actually, using this data, you can create a covariance matrix or you can create a correlation matrix, right? By using this raw data, right? This is the example of a covariance matrix. And this one is correlation matrix, right? In this case, so you need to specify the mean and standard deviation, right? For each, these ones, right? For each variable. Right? As I said, the easiest way is to use the raw data, right? Now let me show you how to use Amos, right? This is the Amos. So I'm going to show you how to do the confirmatory factor analysis and also the analysis for the structure equation model, right? Now let's first try to do the confirmatory factor analysis. Remember that we had three latent variables, right? EP, AC, OC. So what you want to do is you want to draw graph first, and then you connect your graph to the data file, and then you do the analysis, right? So what you want to do is that you click this one, right? And then you draw a circle here, and you click once, twice, 3 times, 4 times, because EP is measured by 4 things, right? Now you draw a graph for the AC, right? Same thing here. You draw a circle, and AC is measured by 4 things, right? Also, and also you draw a circle for OC, right? And also OC is made by 4 things, right? Now, if you turn, if you rotate this thing, right, and you click this one, okay, and you rotate this thing, right? And also you can rotate this thing, and also you can rotate this thing, right? And then you want to specify the correlation among the latent variables, right? You click this one, and you connect these latent variables, and also you connect this one to this. Also you connect this one to this, right? So these variables are correlated, right? And once you draw, this graph, you need to connect this graph to data file, right? So you go to the file and you select data files, right? And then you specify your data file, right? So in my case, I have here, this one is the EPACOC data, and open. Okay. Now, if you wanna see your data, you click this one. So, this one is the covariance matrices, right? This is not the raw data, right? So you close this one. And you click OK, right? So your graph is connected to data file, right? Now, once you did that, so you name, these things, right? So first you click this one, right? If you click this one, you see the variable names, right? From your data set, right? You move this one to here and this one to here and this one to here and this one to here, right? And here, right? These one the variable names, right? And also you need to name these errors, right? So in this case, you click this one and you type let's say E1 here, right? Okay. And you click this one and E2 and you click this one E3 and you click this one E4 and you click this one E5 E6 E7 E8 E9 E10 E11 E12, right? Also, you need to name the latent variables, right? So you click this one, EP, and this one, AC, and this one, OC, right? So everything is named, right? And before you do the analysis, right, you need to specify the output, right? In order to do that, you go to the view here, right? And you select analysis properties, right? And actually you can specify the method. We are going to use maximum likelihood, right? And you go to the here output, right? And you check the standardized estimates and correlations of estimates, right? You can check, many other things, right? But these are the critical ones for computing ABEs, right? And you close this, and then you do the analysis. You select analyze, and you select calculate estimates, right? And then you need to name the alpha file name, right? So let's say test2, okay? And save. So the output is very quick, right? So we have already the output here. So in order to view the output, you go to the view, right? And then you go to the text output, right? And then if you wanna get the estimates, you click estimates, right? So in this case, you go to standardized estimates, right? These are the standardized estimates, right? And also you get the correlations here, right? And you get the error variances, right? Here. This is the output for the conformity effect analysis, right? So by using, these numbers, you can compute the AVEs, right? Now, we are going to check the model fit when we do the, actually the analysis for the structural model, right? In this case, it's a model fit. If you go to the model fit, you can get all the data here, right? So, for example, in this case, we'll talk about this one, chi-square values and the GFI and the AGFI, or things like that. But for the component effect analysis, this is not that important, right? So we are going to deal with these things when we do the structure model analysis, right? Now let's do the structure equation model, right? So same thing, you graph first, right? So you click this one. So make circle. And you draw circle and draw circle. Right? And then you are going to rotate. You are going to rotate. Okay? And we are going to specify the relationship here. Right? And also the correlation. Right? Now, in order to change the direction here, you click this one, right? Actually, you can change the direction here, right? And then you need to name these variables, right? In order to do that, you need to connect this grab to data file, right? So you go to file and the data files, file name, and we are going to have this one, right? Same data, right? And then you click OK, and you click this one, okay? So EP1, EP2, EP3, EP4, right? AC1, AC2, right? And OC1, OC2. And you need to name, these latent variables and errors, right? Before we do that, I want to mention one thing. As I said, these variables are the independent variables, right? And this one is dependent variable, right? Because error comes from this and from this, right? So this is dependent variable. In case of a dependent variable, right, you need to add errors, right? So you need to have errors for this. So in order to do that, you need to click this one, okay? This one. And then you go here and then you add error here, right? We had errors for the each of these variables, right? These are the errors, right? Okay, because you see the errors come from here and from here, so we had errors, right? Just like that. So since this one is dependent variable, we need to have error, right? Now let's name these things. E1, okay, and we are going to name this one E2, this one E3, this one E4, this one E5, this one E6, this one E7, right? So once you enter these things, right, you go to the view and analysis properties, standardized estimates, correlations, right? And I'll talk about the modification indices later, but let's check this for the moment. Now you click this. So you go to the analyze and the calculate estimates. And let's name this one okay, and click this one, right? And if you check this one, right, you will get the pass coefficients here, right? Okay. Now you go to the view and text output, right? And you go to the estimates, right? You get the pass coefficients, right? Okay. And if you go to the model fit, you will get the all the statistics here, right? So chi-square value, C mean is chi-square value, and you have a GFI and things like that, right? So we'll talk about this one later, right? Right now, it is important for you to to know how to draw graphs and how to connect your graph to the data file, and then how to do the analysis, and how to specify the outputs, and how to view the output, and those things, right? We are back to PowerPoints. So I showed you how to do the confirmatory factor analysis and also the analysis for the structural equation model, right? Once you get the output, you need to know how to interpret the output, right? So we'll talk about this one next time. Let's stop here and see you next time.